Listen to them. They're already excited about it. Rotational symmetry and rotations. The last geometry lesson of the year. Okay. What do you know about rotations and symmetry? If you're going to rotate all the way around, how many degrees is that? 360. Any snowboarders in here? They all talk like that. No, I'm just kidding. They don't. Any skateboarders in here do 360s on your skateboard? All the way around, okay? So let's talk about rotational symmetry with this shape right here. This shape is a square. And basically rotational symmetry is if you're going to rotate this object, you tell me when it gets back to its normal orientation. So if I rotate this and it gets back to its normal orientation, so we rotate this 90 degrees and it clicks into itself. I rotate another 90, click. So every time I rotate this object 90 degrees, it maps right onto itself. That's why we say this has 90-degree rotational symmetry. What's the rotational symmetry? 90 degrees. If you go from the middle, you take the center of this object, and you go from this vertex here to that vertex there, and you rotate it. Okay, that's a 90-degree rotation. Boop. Okay. So we say that object, that square, has 90-degree rotational symmetry. What is this?
A triangle.
Good. And it's an equilateral triangle. That means every angle in here, if it's exactly the same, every angle in here is 60 degrees, right? So we have 60 degrees there, there, and there. So how many degrees is this going to take when it rotates to map exactly on this in the same orientation that it is right now? It's not going to be 60. It's going to be more than 60. How many? Think about this for a minute. How many degrees is it going to take to rotate all the way around? So if you follow this part right here, let me see if I can change the color of this for a minute. Let's go to gradient fill. Okay, good. Blue was good. All right, if you follow the white side right here, the little white part, how many degrees is it going to take to rotate it to get it back to where it started? Right, I went all the way around, 360 degrees, and I'm back to where it started. How many degrees does it take for the white part to be up here? 60 or 120? How many degrees from there? Well, it's I think I moved it or something. Yeah. I'm moving it every time. Maybe.
It's rotating not from the center. That's rotating from
Yeah.
the main point.
Yeah. Okay, so it's not rotating from the center. Let's get rid of all these. But if I break this triangle down from the center, and I take the center, and I go out to each point, I'm talking about 120-degree rotation from each spot. So we'd say that this equilateral triangle or an equilateral triangle has 120-degree rotational symmetry. Okay, let's look at some different objects. What?
Where'd you get that picture?
Is it appropriate? I don't know. What's inappropriate about it? It's a leg.
It's 3 legs.
God, you guys are sensitive. All right, so if I rotate this, how many degrees is it going to take for it to get back to, the same orientation? So what I mean is, if this leg right here, if this leg up here is kicking right there, how many degrees is it going to take for me to get back to that spot? And, it's not rotating from the center, but if it was, it would be like that. And that would be how many degrees? 120 again. And this shape is based on like a triangular pattern. This is based on an equilateral triangle. Therefore, it has the same exact rotational symmetry as the triangle that we just looked at up here. That triangle, that shape, they're about the same. So this we'd say has 120 degree rotational symmetry. 120 degree rotational symmetry. That means every time you rotate it 120 degrees, it's going to map onto itself or lock in the same exact orientation. I made this last night.
Oh, you made it. Oh.
Yeah. Yep.
Awesome.
I got some spray paint out in the garage and I made it. So how many degrees, you would say this has rotational symmetry, right? If I rotate it a certain amount, it's going to
It's rotating from the center.
lap onto itself. It's going to map onto itself. I figured why this isn't rotating exactly the same is because the actual shape here is a rectangle. If you look at the outline of this, see there's the outline here. The shape of the outline is like rectangular, so it's not a square, so it's not, if I click on that, see? So,
The outline is a square.
so when I rotate this, maybe the other one was. Is that a square?
Yep.
That's not a square.
Yeah, it is.
No, it's longer. It's longer too. So how many degrees rotational symmetry is this? What shape is this based on?
Octagon.
Octagon?
Whatever has
I don't know. Let's count them. Septagon?
whatever 7 is.
How many little blades on this throwing star? The patience level in here is just extraordinary. Stop sign has 8. So this is a little bit different than a stop sign. It has one less side, but it's based on like a regular septagon. So if I rotated this, how can you tell how many degrees you have to rotate it before it maps onto itself? What are we doing here? Well, how many sides? When we went up to the square, how many sides does a square have?
4.
Okay, so if we take 360 degrees, full rotation, divided by 4, you're going to get your rotational symmetry. This is a regular triangle. You take 360 divided by 3, you get your rotational symmetry there. It's not always the case, but with a regular polygon, that's what we're working with. So this has a rotational symmetry of 360 divided by 7 degrees, which it doesn't work out perfectly. It's like, I don't know, if you do 50, you get 350, and then you got 10 degrees to make up for. So 350 and 10 sevenths. So 351 and 3 sevenths. So roughly 351 degrees, or 51 degrees. Okay, that's rotational symmetry. You guys think you understand that? Any questions on rotational symmetry? All right, the next part to this section is just rotating some object around a center of rotation that is not inside the object. The other, in rotational symmetry, the center of rotation was like inside your object. If you look at this, where's my center of rotation? Where am I rotating this around? Well, the center is like right in there. So then I just start rotating that around the center. See? And as I start rotating it, my center moves a little bit. So that's why it wasn't perfect there. But down here, now we're going to rotate this triangle around a center of rotation that's not inside the triangle. So we're going to go through a process of creating a rotation here with a compass and protractor. And this would be on the back side of your yellow sheet. So on the back side of your yellow sheet, there are 4 rotations. So you need to grab, if you don't have your own, I have some here you can use. And the compasses are a little light, so you might need to share. But come grab a compass and a protractor to use for this rotation. Okay, so this is the number 1 on the back side. We have a triangle, and we're going to rotate it 60 degrees clockwise. So what we need to do here is connect each vertice of this triangle to point C, and I'll do one at a time. So you want to make a line from A to C. So we'll start by putting a line in from A to C. Okay, so you connect your line from A to C, and what we want to make is a 60-degree angle in a clockwise direction at a center of rotation, which would be the vertex of our angle at C. So I take my compass here and my protractor, and since I want to measure that angle, this is not the best background here. Maybe I'll change the background. We'll do that there. Now we can see a little better. So I want to take this protractor and I want to center it on the center of rotation, which will be the vertex of our angle, and I want to make a 60-degree angle with the line AC. So I'm going to make a mark up here at 60 degrees. And then what I do is I connect that then. So now I'm going to go and take that and I'm going to connect C, if I can get this thing smaller. How did I do that? There we go. So then I'll get this smaller and I'll connect C to that point I made, and now this is a 60-degree angle. And it's 60 degrees in the clockwise direction. If it was counterclockwise, it would be located down below C. So what I mean by that, I guess, is if I rotate clockwise, I'm going the way the clock goes, this way. If I were to go counterclockwise, I'd be going downwards this way. So there is a 60-degree clockwise angle I made with segment AC. Now I need to do is mark the distance from A to C. So I'm going to take my compass now, and a compass is like it's like a measuring tool, but it doesn't have any units on it. So we can preserve distance with a compass. And I'm going to rotate this here and measure the distance from, I don't want to move that. I want to move that. I want to move that. So there is the length of AC. So when I make a mark on that 60-degree angle, that will be the same exact distance. So I'll go up here and I will make a mark. Or I'll try to make a mark. On that ray. And the mark on that ray then will be the same distance as AC was. So now I have a point up here. This point is like A prime. It's my new A. And I do that same process for every vertice in the object that you are going to rotate. So now I do the same exact thing with CB and CD, and each new yellow prime point, when I connect them, will be the exact same triangle as ABD. It'll be the exact same size triangle, just be rotated. So we'll go ahead and do each vertice. So now I make a 60-degree angle with my line CB. So once I connect CB, I need to take the protractor again and move it over. And mark a 60-degree angle. It's good to make it a little longer because I'm not quite sure the length of CB until I get my compass out and measure it. So bring your compass over, measure the length from CB. And then we'll go and rotate it and make a mark on the black new ray that we made here. And that will be our new point CB prime. Get that out of there. Now I have my new point B prime, which has been rotated 60 degrees. See, this is a 60-degree angle right here. It's been rotated. And I have one more point to do, which is CD. Last line here we'll connect in white, and we'll connect C to D. So if we connect C to D, and then we measure that angle, make another 60-degree angle there. Whoops. Take our protractor. Hey, can you gentlemen here, Michael, can you zip it, please, so we can finish this? So, same thing all the time. 60-degree angle there would be down here at 60. Mark it. Get rid of this, put our line in. I wanted that line white. Okay, so there's another 60-degree angle, just like all the rest. So that's 60 degrees there. The black angle is 60 there, and the gray angle is 60 right there. They're all rotated clockwise 60 degrees. And then we just need to preserve the distance here. That's what we use our compass for. So we'll see how long, whoops, how far it was. Here. Whoa, we got all sorts of stuff going on now. Let's go back. Oops, measuring the wrong part. That's funny. I need to measure this. So there's the measure of the distance from C to D. So now I'll rotate that and mark that on this line here. And if I make a new yellow mark here, this is my new point. What is this point called right here? D, that's the new one, D prime. So now if I connect A prime, B prime, and D prime, that should complete the 60-degree clockwise rotation of the whole triangle. So we'll go ahead and connect all those together, and we'll make the line a little thicker, and we'll make it bright green. So let's connect D prime to B prime, B prime to A prime, and there you have a triangle. It's our same triangle that has been rotated 60 degrees around that center C. So this original triangle here, where it was rotated around this point, this red point right here. I can't really move it because I got too much other stuff in the way. 60 degrees. Okay, any questions? So there's 3 other rotations that I want you to do on this yellow sheet, and then on the other side some stuff from circles from yesterday. So that's a wrap.